Allotropes are versions of an element that are different based on how the atoms of the element are bonded together. Right? So we talked about compounds being different elements that bond together in certain ratios, and they're connected in a certain way, and the electrons are arranged around them in a certain way, and that's what defines a compound. But elements can also be found in different forms depending on how they're bonded together and how the electrons are arranged around them. So when we think about oxygen as an element, we think about the element on the periodic table, O. But for oxygen, there's a number of ways it can be found in nature and form. One way is to have it pick up a couple extra electrons and take on a charge. Right? So we talked about making ions, and we know to make an ion, to give it a charge, generally it will pick up or lose as many electrons as it needs to make the same number of electrons as a noble gas, which would be neon in that case. So that's one form for oxygen. But when we think about it, with 8 protons and now 10 electrons, that's a bit of an imbalance in the ratio of positive to negative charge. So it might not be super stable. So what's the most common way you'll find oxygen in nature? If it's just oxygen, yeah, you'd find it as O2. But what's the most common form that we find oxygen in on Earth? Yeah, it's part of water, right? So if I think about that, if I compare the O2 minus with water, in water the oxygen has 2 bonds. So what are those bonds? They're actually pairs of electrons. Right? So if I think about from the point of view of the oxygen, the number of electrons around it is the same in water as it is in an oxide ion with an O2 minus charge. The difference is, in water I'm bringing 2 hydrogens around, and what's inside a hydrogen? 1 proton. So basically water is really not that different from O2 minus, except it's a lot more stable, because when I have water, the normal 2 minus charge that the oxygen would carry from having 2 extra electrons is balanced with the 2 hydrogens, protons, so that the overall structure doesn't have any charge. So the most abundant things in nature generally are situations where the charge isn't very imbalanced, especially in terms of the ratio of positive to negative. And so that's why we see oxygen so often forming a molecule where it's sharing electrons with hydrogen, because the hydrogen has the charge it needs to balance out its charge. O2 was mentioned, so that's another form. So since this is water, it's a compound, it's not considered an allotrope. Allotropes are versions or forms or varieties of an element, not for a compound. So that's just what the word means. So you could say that O2 minus is an allotrope. If you had a neutral oxygen with 6 electrons around it, that's not going to be that stable, because there's space in the second energy level to bring in more electrons, and it doesn't have the same number of electrons as a noble gas. So instead of just picking up 2 electrons and holding them by itself, another oxygen could come in with its pair of electrons. So now I have 2 oxygens with 6 each, so I still have a total of 12 electrons. So I haven't created any charge imbalance, because the electrons I have there are the number that each oxygen would normally have to keep its charge balanced and neutral. But what I've done now is, if these ones in the middle get shared between the 2 oxygens, this oxygen has 8 around it, which is the same number as a noble gas. And since these 2 in the middle are shared, this oxygen also has 8 around it, which is the same number as a noble gas. And so both oxygens get satisfied with their noble gas configurations that way. So that's one allotrope, one version of the way the element oxygen can be found. That's formula for that is O2 because there's two oxygens in that. Another allotrope for oxygen is O3. So I can also make a molecule, which is a group of atoms that are sharing electrons through covalent bonds, which we'll talk more about today, by sharing electrons between the oxygens, and I can make one with 3 oxygens. So if I bring an oxygen in here with 6, and I bring another oxygen here with 6, and another oxygen here with 6, if I put them in just the right way, I can allow them to share the electrons and each make a noble gas configuration. And that's really what we're going to talk about today. How to draw structures that allow the oxygens to share their electrons and make noble gas configurations. And for some elements, so specifically for an allotrope, we're talking about different options for elements when there's only one element from the periodic table involved in that combination of atoms and electrons. Those are called allotropes. So O3 does not actually involve a triple bond. So if you look at the sharing, so this oxygen here has 2, 4, 6, 8, right? It needs 8 valence electrons to make the same number as neon to get a noble gas configuration. So for that oxygen, since it has 3 lone pairs, it only wants to have a single bond, a single pair of electrons between it and the neighboring oxygen to make a total of the same number of electrons as a noble gas. If you look at this oxygen on the outside, since it only has 2 lone pairs, or 2 pairs of electrons that are owned exclusively by itself and not shared with any other atoms, it needs 2 shared. So there would be a double bond between the 2 oxygens on the right and a single bond between the oxygen on the left and the middle oxygen. But this middle oxygen is clearly different from the other 2 because it's connected to both. It's sharing 1 pair with this oxygen and 2 pairs with that oxygen. That is the way you would get O3, which is ozone, to make noble gas configurations or give each oxygen the same number of electrons as neon to share.